vectors actually are doing something complicated.
Yeah, but I suppose it's still nice that you can just find that this is present in all the terms. So I don't know how correct this is, but could you do something like that? So like 1 over rad 2 minus rad 2 1, something like that.
There's a sign here, so I would not take it out.
Oh, right.
Yeah. Theta is equal to the phi of theta at phi equal to 0 times cosine omega of phi plus the sine of theta 0 times, and here we have v phi times the sine of omega phi, and v phi, and this is a function of phi, is equal to v phi at 0 times cosine omega phi, and here we have minus 1 over sine of theta 0 times v phi, and this is also at 0. Sorry, this is v theta at 0 times sine of omega phi.
Oh, that is a phi, right? Oh,
yeah, I'm thinking in terms of phi. Good. And so there's a theta and a phi, and now you can write it.
You just rewrote what we wrote over there, right?
Yeah. So now you can write it in a matrix form: cosine omega phi, sine omega sine of omega phi, cosine of. Oh, I should write on this side. I want to write v theta at 0, v phi at 0, and so that's sine, and here now v phi of 0. So this, that goes to the theta component, that is 1 over sine of theta 0, and here there's, I forgot to write this sine theta 0, and here there's 1 over sine theta 0 times sine omega phi, and the last one is cosine omega phi. So this is the matrix notation, and omega was cosine of theta 0. So if we now look at maybe one case, if you look at the case when on the equator,
so theta naught can be
theta is not 90 degrees. That means that omega is equal to 0, and then this is 1. When omega is equal to 0, this is equal to 0. So you see indeed nothing happens. However, in other cases, something happens. Then the vector actually changes. So you could look at, I know, we could look at what omega do you like? What theta do you like?
Yes, something like 45 would be fine.
45.
To have cosine and sine.
We can try that. Then it's already quite. Then theta, when theta 0 is say pi over 4, then cosine theta 0 is 1 over square root of 2, and there's also sine of theta 0. So what do we get here? So we get cosine phi divided by square root of 2, this becomes sine theta 0 becomes 1 divided by square root of 2 times the sine of phi divided by square root of 2. This becomes minus now square root of 2 times the sine of phi divided by square root of 2. And here we get the cosine of phi divided by square root of 2. And this acts on the initial vector at time 0.
Wait, have I confused omega and theta naught?
Now omega is cosine theta naught.
Oh, okay.
And now we can look at theta is 2 pi. And what you see is when theta is 2 pi,
that would be the same as theta equals 0.
yeah, no, and not sorry, at phi equal to 2 pi.
Okay.
So that means we went around once. And then you see these are not nice angles. That's like pi divided by square root of 2. So what you see is that the vector is actually mapped to something else. And it's a non-trivial linear combination of the two. So because the space is curved, the vectors actually are doing something complicated.
Yeah, but I suppose it's still nice that you can just find that this is present in all the terms. So I don't know how correct this is, but could you do something like that? So like 1 over rad 2 minus rad 2 1, something like that.
There's a sign here, so I would not take it out.
Oh, right.
Yeah. So.
But yeah.
So you cannot you cannot really.
So you can't really do anything.
You can play a little bit with it. You can write this in different type of matrices, and maybe I can make it to work. So what you could do is, I'm trying to make it work to work.
Yeah, because eventually you end up having to take like cosine of cosine, which is not nice unless you.
So we have 1 square root of 2, another matrix 1 over square root of 2, zeros here and there, and in between here we get the cosine of phi, the sine. Then that's we had. Let's write here omega 0. That's simpler. We could write phi divided by square root of 2, and then here we have the sine of phi divided by square root of 2. Here we get minus the sine of phi divided by square root of 2, and here we get the cosine of phi divided by square root of 2. And I think this times that is okay. This times that gives 1. This is the 1, 2 element. Then we get here the 1 over square root of 2, and the 2, 1 element, then we get that.
Is that a rotation matrix?
Exactly. This is now a rotation matrix. So what you do is, you see there's maybe some stretching of the vector by a square root of 2. Then you rotate it, and then you unstretch. Or you contract the vector, and then you stretch it again afterward.
Yeah, that's definitely interesting, but it's not going to end up looking nice for anything except like 90
oh, that's right.
plus 180n, because you have cosine of cosine of something.
Yeah. No, generally it is not really nice. Right. And so what you learn from this is that parallel transport is really non-trivial. Even the simplest examples we can actually think of. It is actually already a lot of work to work it out. And
So it's not exactly easy to come up with a good meaning for some arbitrary theta naught.
no. And the other thing we want to try is we could try are the geodesics. And that is how a free particle would move on a sphere.
Right.
And for the geodesic equations, we basically have all the information. It's an equation in terms of the Christoffel symbols, right? So it's a geodesic equation. And that is d squared x mu d lambda squared plus gamma mu sigma rho dx sigma d x lambda d lambda dx rho d lambda is equal to 0. So it's in this equation, geodesic equation. And basically we can try to solve them because we now know the Christoffel symbol. We can.
And we're only dealing with the two coordinates, theta and phi.
We have two coordinates.
And one of them is a constant.
Lambda, we don't know what it is. What you would think if you have a sphere, you think the equator is geodesic.
Well, probably, because it's kind of like a straight line around the sphere, like a great circle.
Yeah. So a geodesic is a curve along which the tangent vector is parallel transported. And that indeed happens like that. So indeed, any great circle, you expect it to be a geodesic.
Right.
And that is...
So the great circles are where theta doesn't change, but only phi changes.
In great circles, it depends on your coordinates. If you don't change your coordinates, this is actually complicated already.
You can't change theta and phi to kind of like rotate it so that, well, I guess that would
you have to change the coordinates so that
because would be bad when you're working with multiple circles.
Because you really know that the choice of coordinates is arbitrary. If you consider this great circle, you as well could have run phi along this direction.
Does that mean that soon we're going to have to deal with theta as a variable as well?
I don't think so. I think these are the only geodesics. I actually didn't work it out myself, so but we will have to solve this equation.
Okay, that should be fine if we just have one variable.
Maybe that's a good homework problem to solve this equation. You know the Christoffel symbols. There are only two variables, theta and phi, and to get started, you can show that the equator is actually a solution of this equation. The equator is theta equal 90 degrees. So theta is constant.
It seems like theta equals 90 degrees is a solution of everything in this way.
No, that's what I take. So that's the equator. Theta is equal to 90 degrees. And if you look at the equator, so the equator is characterized by theta is 90 degrees, this pi over 2 comma phi. So that is the equator. And if we choose lambda, lambda we choose equal to phi. And we can maybe already see it. So if you look at the
right.
theta.
It's good that we can choose lambda because it's an arbitrary coordinate. It's pretty much anything we want.
Yeah.
in terms of theta and phi.
So if you so the vector only has a phi component, there's no theta component, and that's good because we can d phi squared d phi. So this is the phi component. So that's actually equal to 0 because the second derivative. And so that means if this is phi, gamma mu, and which component of this is now the phi component, which are non-zero of the phi components, you still remember?
I'm pretty sure it's phi, phi theta, phi, and phi,
Yeah,
phi theta.
and then you get here d theta, d phi, okay, d phi, d phi. And of course, this is equal to 0 because that vanishes. So you see that the equator is actually a solution of this geodesic equation.
Right, and then we have to do it for an arbitrary pi over 2, not just theta, not just pi over 2.
Yeah, yeah. Maybe if you have an equation, a great circle through the North Pole, that's also a simple case in these coordinates. Because then
you're just varying theta and not phi.
Then indeed. So
or you can just change your coordinates so you're varying phi again and theta is constant.
So if you go through the North Pole, then so here's theta, here's theta is pi, but you have two different values of phi.
Right.
So on one half you actually have a different phi than on the other. Right. So it's a little bit more non-trivial than you would think to start with.
The most interesting one would be the ones that don't contain a diameter.
Yeah, you would think they are not solutions of this geodesic equation.
But they're a Greek circle, aren't they? Well, it's
so the condition is that the tangent vector is parallel transported along itself. So if this tangent vector is parallel transported, so we would have to look at this at parallel transported. The tangent vector in that case is only a v phi. And so the theta component, if you are here, is equal to 0. There's only a phi component. If you make this equal to 0, then you see after parallel transport, there can be a theta component. So it is no longer a tangent vector.
Okay.
So that is not a geodesic.
So the only geodesics are the ones that contain a diameter.
I think so. I think so.
I see.
Okay.
I'll try to get back to you by the time we meet.
By what?
By the next time we meet.
Yeah, yeah. So that's an important thing. After parallel transport, we can look at curvature and how you calculate that using the Riemann tensor. And but parallel transport, you have to understand that well because that's really the basic of differential geometry. And
this definitely feels more conceptual than just force deriving all of those four vectors.
Yeah. No, you have to do both. You have to do be able to do the handwork, derive it by just doing the calculation, and also kind of understand that by guessing, basically you know what the geodesics is, to have an intuition for what it means.
All this math and such a large chance of making an error must have taken a lot of patience, especially when they didn't have computers to check your work.
Oh yeah, oh yeah. Now I use Mathematica to check it.
Yeah.
And